So good morning to everyone here, to everyone online. I just wanted to make a brief announcement. So not only as coordinator of Project SALTOpower, but also as responsible of the research facility at EVER Molten Salt platform. We will be opening different positions, mostly for PhD students, but also some for researchers on the topics related with molten salt technologies. So both on Carnot batteries, high temperature storage, connection with solar thermochemistry. So we will be using your email addresses that we received from your registration to announce these positions. So for those who might be interested, pay attention to your email. Most likely within the next 2 weeks, we will be sending you some information about these possibilities. Okay, that was my announcement. Thank you so much for your attention. And
Yes, we can start again the second session of this morning with Christian Odenthal. He is mechanical engineering. He holds his PhD at the Institute of Energy Storage and Institute of Engineering Thermodynamics. He is a research fellow and project manager at Institute of Engineering Thermodynamics in DLR in Cologne. And his presentation will deal with molten salt thermal energy storage from current two tanks systems to thermocline technology.
Yeah, thank you for the introduction. Welcome, everybody. Sorry, yesterday I didn't manage to transform my presentation into the template. Maybe I can do it afterwards. So I'm using the DLR template now. So this is just to give you a brief overview of molten salt thermal energy storage from the state of the art, the two tank system, to the single tank research topics we currently focus on at DLR, and some examples which have already been done in that field. So regarding the two tank system, I think most of you are aware of its existence, and I think the working principle is also quite simple. You have two tanks. They are filled with molten salt. Typically, the so-called cold tank has a temperature of about 300 degrees Celsius, and that salt is extracted from that tank and heated up to a higher temperature. That can be, or typically is done in concentrating solar power plants. But that can also be in newer fields of application. For example, an electric heater. Thomas will later show some examples in his presentation about that topic. And yeah, and so basically that can be done directly in a solar receiver or in oil-based solar power plants. That's done in a heat exchanger, where the heat is transferred from the primary HTF to the molten salt, and then it is stored in a second tank, in the hot tank. If you have an oil-based system, you're limited in the temperature of roughly 400 degrees. These newer solar tower plants go up to 560 degrees. And for discharging, the process is simply reversed. So you extract the hot salt from the tank, divert it to your power block, for example, where you generate electricity, for example, and then you have the salt again at 300 degrees and store it in the cold tank. So here are some examples. The left one is one of these oil-based power plants via DOS, which is a parabolic trough plant. Here you can see between these big two tanks, there's an arrangement of heat exchangers. And the other example is crescent dunes, where you use the salt directly also as a heat transfer medium. And after heating it up in the solar tower, it's stored directly in those storage tanks. Now, what we are looking at DLR is these so-called single tank thermal energy storage concept. And here you store the hot and the salt, the cold molten salt together in one single tank. And that is working because hot salt has a lower density than the cold salt. So the difference is quite high. It's about 10% in density difference. Because of that, you can have the cold salt on the bottom and the hot salt on the top. I always compare it with a latte macchiato. So there you also have cold milk and you put hot coffee on top and it remains stratified unless you start stirring it. And here you see basically the working principle of the system. So there's a laser pointer. Oh, yeah. Okay, so you can extract the cold salt from the bottom with a pump and simultaneously add hot salt at the top through a distributor ring. And then over the course of the time, as you extract the cold salt and add hot molten salt, you end up with this situation that you have the tank completely filled with salt. And what you can also observe in that case is because of the higher, the lower density of the hot salt, you will have a higher filling level on the tank after the end of the charging process. There are some advantages of this concept. The first one is with the two tanks, you have obviously about 50% of the volume is unused. You have a high volume of gases, which you have to manage. And in that case, this volume is clearly reduced. Another aspect is in the two-tank system, you always have to completely empty the tanks. So the pumps need to have very long shafts. And in this case, since you always have some liquid level in here, you can use short shafted pumps, which are much less cost efficient, costly. And also in those two tank system, you always have a liquid heel remaining inside the tanks, and which you simply don't use. So if you think of a filling level of say 10 meters, and you have 60 centimeters or more of unused volume, that is it's not 10%, but it goes into this direction. And if you have just a single tank, you have this only once. Yeah, the next slide just shows the discharge process. It's basically simply reverse. So you put in the cold salt from the bottom, you extract the hot salt with this top pump, and by doing so you can discharge your system and you end up with a lower filling level. Yeah, some other advantages of this concept is that you basically have in total a lower volume of your system, and I think that's probably not so important in the case of CSP applications, but we are also looking at applications where you could use this concept in chemical plants, for example, or in conventional power plants for flexibilization. And in these cases, mostly you're very limited in the land use. And if you can save the land use of a complete tank, it's a very huge advantage. This pure thermocline concept, there has already been a larger demonstration in the Mats solar power plant in Egypt, where this concept was tested. There's an example, a picture showing this tank. Yeah, so that is basically the pure thermocline concept. There are two other concepts we're also interested in at DLR. the first one is the thermocline with a moving barrier. So what you do here is basically you add in a floating insulated layer, which must have a density which is a bit lower than the cold salt. So it has to float on cold salt without sinking, but it has to be a bit heavier than the hot salt, so that it sinks down in hot salt. And then you have a physical separation layer between the hot and the cold salt. And during operation, that that barrier needs to move upwards and downwards, obviously. So that's also something you have to bear in mind. But because you have a better insulation between the hot and the cold layer, you actually don't use molten salt as insulation. You can again reduce the complete height of the tank a little bit. And also what's an aspect is that you have to care less about any possibilities of mixing effects during the operation. There's also been in this via DOS power plant a demonstrator, but there's very little information available about the outcome of the project. And we tested something like this also at DLR, but we had some issues with the moving barrier. So yeah, we didn't get any cyclic operational results from that. And yeah, for us, one of the most interesting concept is the thermocline with filler. In that case, you add cost-efficient solid storage material to the tank. So basically, you substitute as much molten salt as possible by a filler material, but the working principle remains the same. That is or has the most potential, because typically the molten salt costs make up about 50% of the total cost of your storage system. And if you can substitute this pricey molten salt with a very cheap solid filler material, then yeah, there's a huge cost reduction potential. There have also been some demonstrators, one with thermal oil, which went up to 300 degrees. And there was another one also from Sandia, which operated with a molten salt mixture up to 500 degrees Celsius. Yeah, exactly. As I said, so you have much less molten salt, so there's a highest cost reduction potential. And now, from our side at DLR, we have a molten salt test facility where we also look at these three single tank storage concepts. And on that picture, you can see a very basic working principle of our plant. So we have two reservoir tanks which act as a heat source, and we have a cold reservoir tank which acts as a heat sink, basically. And these supply hot and cold salt to our single tank thermal energy storage. And for maintaining the temperature levels, you need an electric heater or an additional electric heater in the hot reservoir tank, and also a cooler in the cold reservoir tank. So if hot salt flows into the cold tank, you need to cool it down, and vice versa on the hot tank. So that is a working principle. On the other picture, you see a three-dimensional sketch. So it's basically a standing tank, which has 2.2 meters in diameter, and a usable height of roughly 6 meters. So so that way we can do experiments in a relevant scale, and we can minimize side effects during the experiments. Yeah, here you can see an example from our testing with a pure thermocline. So we inserted a metal structure with multiple thermocouples inside the tank, where we measured temperature profiles on different axes, as well as, of course, along the middle axis. And so this is, for example, was the first charging cycle during these experiments with a mass flow of 4 kilograms per second. So that is the nominal mass flow we have in our plan. And yeah, in that case, we started off with yeah, almost the lowest temperature level, and then added hot molten salt. And then after about 2 hours, you have a fully charged storage tank, as you can see here from these progression of the temperature profiles. Another experiment we did was then with the filler material. For that case, we have some sort of baskets which we can insert into the storage facility. So these baskets have a perforated floor so that the salt can flow through the baskets actually. And we do that because that makes it much easier to later take out the filler material out of the tank. Otherwise, it would be probably a huge effort to get the filler material out of the tank. And also for placing everything inside the tank. You can do it outside of the facility, and then when you finish, you can just put in these baskets. So there are in total 3 baskets, which can be stacked on top of each other. And in this case, we tested basalt rocks in the size of, with a mean diameter of roughly 1 centimeter. You can see that here on the picture. And yeah, and there we could successfully also test this thermocline concept with the filler material. You can see from the difference to the pure thermocline that there's also some heat transfer going on between the salt and the solid material. So that is also increasing the width of your thermocline region. So basically this transitional region between the hot and the cold salt. And also one important aspect in this with this system is that during operation, due to the heat transfer, but also through conduction, this thermocline region is always expanding slowly. And you can see that on the next slide. There's a small video we created from the actual measured temperatures. So it's just an interpolation basically of the temperature measurements. It's not a simulation. And I can start it. And then you can see as you cycle through, or if you do cyclic operation, that your thermocline is slightly expanding with every cycle. So what you actually need to do or to bear in mind is that you need to extract this thermocline region a bit. And the more you extract, the more you come close to the initial situation where you start over with a freshly built up thermocline. So that would be the ideal situation, but in that case, you have to think of your exit temperatures of the storage system. So if you extract the thermocline, for example, during the discharge process, then also your outlet temperature goes down. And if you have a power plant process attached to your storage system, that needs to be able to cope with this declining temperature. So there's always a limit how far you can go down. And also on the other side, with the cold side, there's also limits how far you can go up with this temperature. But from this thermocline perspective, you want to extract as much as possible, because that is basically rebuilding your thermocline. I can restart the video. If you look at the thickness of the thermocline, and you can see that it's getting bigger and bigger, and the time you can operate one cycle is getting smaller and smaller after you reach some sort of steady state. That is something you have to look at, yeah, also from the system, so from the system level. Yeah, that's it from my side. Thanks. Yeah, please.
What was the result in terms of effective capacity?
Yeah, there
On
oh, okay, yeah, sorry. So the question. Yeah.
Answer this, you need to specify what is the tolerance of the outlet temperature set for.
Yeah. So the question was, how far, what change of outlet temperature you can tolerate? Yeah, and that's very difficult to answer because, so, for example, if you think of this thermocline extraction thing, you can do it on two ways. You can go completely down with the temperature so that you have completely discharged your system to 300 degrees. Then you need to look at your power plan, how it can deal with it somehow. Maybe you can, there were some ideas of using the heat for the power plant as far as possible, and then you can maybe use the next morning some heat for preheating purposes. Also, if you have a solar field, you could basically allow higher inlet temperatures, and you need to defocus some collectors maybe. And also, if you have an electric system that is completely changing many parameters you have in CSP plants, if you have an electric heater, it doesn't really matter. You can go up with the temperature during charging. You just regulate down your electric energy, and then you could completely heat your system to I wouldn't say uniform temperature, but you can extract on the other side a lot of a big chunk of the thermocline. So I think there is a huge field you can play with. I mean, as you saw, the packing itself was about 5 meters, and the thermocline is initially in the range of 1.50 meter maybe. But if you do nothing, if you keep it completely inside, it will expand more and more. So at some point you need to come up with an idea how to deal with it. But I would say it really depends on your system, what you have attached to.
Yeah, I mean, to show that would work really here. That's the reduction of.
Yeah.
So they just give us the result. Not that much. We did a work with integration. Production, something like 10 or I'd say. Was it 1.50 meter? Was it 1.50 meter in a 12 or 15 time?
Yeah. So in our case of the thesis facility, yeah. So if it's 10 meters in height, then 1.50 meter is less. And then also, as I said before, the liquid heel you only have once in a single tank plays a role, and then by the end of the day, there's things get much better than you think initially.
Just to make sure I got it correctly,
you simulated, for instance, 1 year operation of a CSP plant implementing a thermocline, a packed beds thermocline, and you have seen that you are losing basically the exploitation factor of the bed is 90%. But what is the tolerance, the temperature tolerance of the turbine in this case?
10 degrees or something like this.
Yeah. I mean, the effect of the extraction of the thermocline is decreasing. So it makes a huge difference if you have only 10 or 20 Kelvin allowed change in temperature. But above 50 Kelvin, 60, 70, there's not so much difference. So between 100 Kelvin and 200 Kelvin, there's almost no difference anymore. Yeah.
Because that's only a follow-up question. So could you compensate this effect of decreasing temperature when you push up the thermocline by, for example, implementing something like an electric heater just for this whole salt that you're extracting,
Yeah.
that the turbine is not suffering from a delta T in your steam temperature?
We haven't looked at this yet, but yeah.
Theoretically, it should be possible, yeah.
Yeah, at least if you have systems where you have an electric heater anyway.
And from another question from a mechanical perspective, so if I compare it with the salt tank, state of the art, they are something like 40 meters high, more or less. And as you said, the fill level is
No, they're not 40 meters high.
14
Yeah, okay.
meters high, and the fill level is typically in the range of something like 11 meters.
Yeah.
Now, if you would apply the same size of tank, would you then fill up the tank to the maximum, or would you also apply a fill level to the same height? What are the mechanical restrictions if you go high density fill up?
Yeah, so you would fill the tank up to here with the filler, because if it's higher, then this extra volume, which is so this extra salt you have here on top when it's fully charged, is useless. So so you want to have this this cavity not filled with rocks. If you fill it with rocks, the level would increase even higher with no point. So you would exactly fill it up to exactly this level, or maybe just somewhere in that range.
Yeah, so the strategy is you basically design the tank in terms of maximum fill level for allowable mechanical stress, and then you only increase the maximum height by say maybe half a meter to allow for a certain safety margin.
Yeah.
You wouldn't increase it to a random size because you want to keep the gas main as small as possible.
Yeah.
Just taking the time to remember the people connected remotely that if you have any questions, you can use the question and answer section of your Teams window. But you can write your questions and we will submit it to the speaker.
Can I see the questions?
There are no
Popping up?
questions at the moment.
I have a question.
Yeah.
Have you considered the effects of the charge and discharge regarding the lifespan of the tank, for example, regarding fatigue and corrosion?
Yeah.
Yeah.
Yeah, this is a very very important topic we currently look at. So the one thing is so-called thermal ratcheting. So basically what's happening is your tank gets hotter and you have a loose packing in there, and no one really knows what would happen with such a big tank, and it would probably fall down somehow if there is a gap. I mean, you can easily work out that if you have a tank 35 meters in diameter, that would expand by a couple of centimeters, like 10 centimeters maybe, and then you would have a gap between the rocks and the tank, and then obviously something would happen with the rocks. They will fall down, and then so far it's still okay, but then it's getting colder and the tank is shrinking again, and what's happening then? Are the rocks going to get crushed? Will the rocks prevent the tank from shrinking? That would be a really a serious issue, because then you would have, you know, the tank wants to become smaller again, but it cannot. So you would have plastic deformation. Maybe if the rocks get crushed, you will have some powder after a while, or maybe they just move. And we saw it at our thesis facility. So in the outer region, we saw that the packing gets compressed, but if it remains static or so, you cannot say it. But that's something we currently look at it, and yeah. And also you have a temperature profile, and that is also inside your tank walls, and that's also something you need to look at. We already did it in a project, but so far we don't see any. I mean, there is additional stresses, obviously, but so far it appears to be something you can still handle. So that's not a showstopper here. Good. Yeah, thank you.
The next presentation will be presented by Thomas Bauer. He received his PhD on the topic of thermophotovoltaics in the university in UK. Since 2005, he works in German Aerospace Center DLR in the Institute of Engineering Thermodynamics within the Department of Thermal Process Technology. Since 2015, he is a team leader of the group of thermal system for fluids with focus on molten salt topics on material, component, and system level.
Yeah. Thank you, Anna, for the introduction. Welcome to my presentation. So this presentation will be a kind of a summary. We have heard about most topics already. So I will focus on non-CSP applications. Bulk electrical storage or Carnot batteries. We heard already from Radia some talk about it. Also, what was mentioned, the conversion of coal power plants. And then also we had a talk already on industrial processes. So it's a bit a different perspective, but we have had this topic before. So here on this slide, I show the different application of molten salt. We have heard a lot about CSP. I will not focus on CSP. We have molten salt storage are being used in CSP plant commercially. There are activities in the nuclear field for nowadays, because these plants want to be more flexible is an issue, and also there are molten salts being used as a fuel in nuclear. But I will not focus on nuclear applications. But to give you a complete picture, there's also use of molten salt, but this is on an R&D level as well. So I will focus on coal power plant conversion, Carnot batteries, and industrial process heats. So I put it dashed here, this box, because we know molten salt in the industrial process heat sector since decades as a heat transfer fluid already. So there are reactors available in this field, but not as a storage solution. We have a recent paper published. It's a review paper, open access, about molten salt storage technology for power generation as a summary. So why do we need electrical storage? I show here as an example the German electricity production. And the demand curve is shown here as a black line. This is 1 week in April, is a recent week. And to explain the graph a bit, in red, we have the nuclear power production, and it phased out in 15th of April, where the last electron generated from nuclear in Germany. So there was a phase out of 3 power plants. We have run-of-river plants, steady production. We have biomass plants generating electricity. It's all very steady. And then we have lignite and hard coal power plants. They operate quite flexible in Germany already. We have gas peaker power plants with flexible production. And then we have installed 7 gigawatt of pumped hydro power plants. So our consumption is between 40 and 70. And this is the right scale. 7 gigawatt is quite a small storage capacity in Germany. So it's limited what Germany could do with additional pumped hydro plants. It's the ideal storage solution, but it's limited about the expansion of this plant. And you can see they operate typically already 2 times a day, often in the morning and in the evening. And then we have the flexible production from wind and PV with the midday peak. So what are the challenges here? As I showed, we have less production now because nuclear phased out already. We also have a phase out of coal power plants in 2030 in North Rhine-Westphalia and in the east of Germany, 2038. We have ambitious targets of full climate CO2-free production at 2045. So large targets from the government, and then we have this flexible production from PV and wind and limited capabilities of increase our storage capacity. In addition, is another challenge because our total electricity demand, as the people forecast, will rise because we have to decarbonize the other sectors like the vehicles and the heating sector of the buildings and the industry. So the forecast is that we need 2 or 3 times so much electricity as nowadays. So this even worsens the situation. So then we have different solutions for this. These are gas peakers. We work on grid extension from north to south. Storage is the topic here, load management, hybridization, and also sector coupling with power to X, power to heat mainly solutions. So I will focus on storage and power to heat here as a solution, but there are other solutions. So what storage options do we have? I made a graph here showing different technologies over the duration of storage. And shown here is the indicated total capex of these technologies. And they are quite different, these technologies. If you have batteries, there's a linear increase with capacity and power. So because you can calculate, can use an equation of power-related costs and capacity-related costs. So for batteries, we see a linear increase. If you look at power to gas to power technology with gas peakers and use, for example, methane and gas caverns, we see that the capacity costs it's a very, the slope is not very high because capacity costs are low, but the power costs are quite high because we need PEM electrolyzers, methanization, quite expensive devices for this technology. And the solutions we are looking at with the molten salt storage are typically in between batteries and this power to gas to power solutions in the intermediate range. And whether this is 4 hours or 40 hours or how long we really need, and maybe don't take the absolute numbers, not too serious, but somewhere in between these 2 technologies are useful durations of storage of pumped thermal energy storage or Carnot batteries, liquid air storage, compressed air storage, or we can also think about using existing steam turbines, existing infrastructure. And in these systems, we have lower costs because we use existing infrastructure. This is especially attractive. I also show here on the slide the Sankey diagram of the efficiency. So if we use power to power with a simple electric heater, we are even more efficient than the power to gas to power route. So in terms of electricity generation, this is a quarter, and we have something like 38% here. And of course, most attractive option is to work in combined heat and power mode, where we have a use also for the heat, because then we have a very high overall efficiency. I have summarized in this slide some recent work on the Carnot batteries. I would say this field is growing quite rapidly over the last few years with a lot of increase of publications. And in this table, you can find some review papers. These are only review papers about the Carnot batteries. There's also an IEA annex task led by DLR. This is about to finish. There will be soon a final report on the work, which is also, I think, a nice summary of the work on the Carnot batteries. There's also activities from the Long Duration Energy Storage Council. They have some reports. This is free accessible, net zero reports. Also is a very good overview as a starting point. I think it has been shown by Radia before. In principle, we can have in a Carnot battery with a heat pump and heat engine ideal efficiencies, because you can multiply these two terms and then you would end up with 100% efficiency. But of course, this is not in realistic systems. So Radia showed some numbers depending on the configuration. It's realistic is maybe something like 75% in the best case. If you use an electric heater, you can also have very low efficiencies. I will come now to the second topic of the conversion of coal power plants. We had a regional project in North Rhine-Westphalia. This is already quite some time ago. It was in 2019 and until 2021. So together with a large electricity provider, RWE, and we looked at a coal power plant, a lignite coal power plant with 600 megawatt electrical power. And the idea was to use an existing coal power plant shown here and to extend it with storages. So in the beginning, we looked at molten salt storage, but later on, there was also some interest to use solid media storage system. So we extended the work and also compared it. I would say as a result, it's quite similar. That it really depends what the better technology is. Also, the ceramic storage could be an option in the project. And then in the end, the idea was to have first one module, and you would run the power plant further with one module, and then subsequently add more and more of these storage modules, and finally replace the coal firing after all. So you would not have it anymore. And of course, the interesting thing of this concept is that you have expensive equipment like cooling towers, steam turbines, generation, you have electricity grid, you have people there, you have the space available already, you have permissions, and this would make it attractive to use an existing location of a coal power plant. In the end, it didn't, the project was stopped because the business case was not given. But the whole activity didn't stop. There were other activities with a development agency called GIZ, with the DLR, looking at the market in Chile, and also looking at the repurposing of coal-fired power plants. There's also a public report available here. This was also done with the colleagues from the Solar Institute at DLR, looking at different coal power plants. They identified one very promising one. And now there are some activities going on about the permission and detailed engineering of this coal power plant. There's no final investment decision taken, to my knowledge. I don't have the latest stage, but some months ago, there was no final investment decision. So we don't know whether this will really happen. But the idea is really to replace the coal firing completely and to have a full conversion to a so-called converted coal power plant to a storage plant here. So what can the research do in this field? We heard from Alex already some work about increasing the temperature of molten salt. This was also an issue and the initial starting point that Alex mentioned this for us to look at higher temperature, because this lignite coal power plant had an operation temperature of about 600 degrees steam. So this was not feasible, and that's also the reason why they looked into solid media storage to run it with molten salt. So you would need a molten salt storage system at 620 degrees. And here on this picture, you can see the different power plants, and almost you can, a lot of power plants are fine with molten salt storage, to say this, but some of the power plants have higher steam parameters, and the one we looked at had also higher steam parameters, and especially the modern power plants have higher steam parameters, and these are also the attractive ones for the conversion because they are still new. And of course, if you have a phase out, you would rather use new and efficient power plants and not the very old ones, which are end of life anyway. So from this point of view, it was attractive for us to go into the development of this higher temperature salts. And the approach was already shown by Alex to basically close the system to retain the reactive gases in the system and in this way stabilize the salt. I will come now to the industrial process heat sector. To give an overview, what is state of the art and what are novel ideas. So we have in the industrial process heat sector already some processes with gas firing, heating up molten salt, and the molten salt heats up the reactor. These are basically large reactors with tubes. In the tubes is the chemical reaction, and the requirement is to have a very isothermal process. And the molten salt can do the heating purpose. So it's used mainly as a heat transfer fluid here, not as a storage. Also, if you have exothermic processes, what they do typically in the chemical industry, they extract the heat, use a steam generator, and inject the steam in the steam lines. So this is already known. I would say these are niche applications, a few processes only. Chemical industry is also not very happy to talk and to elaborate about this, but we know that this exists. So the idea now with the storage could be to integrate fluctuating renewable energy, store it, and then supply the heat to the process, similar as it's shown here, but to have an additional storage system. Also very attractive, and I will show an example later on, is to use combined heat and power, because if you discharge your storage, you make use of electricity and heat, and you have very high overall efficiencies. And another approach is if you have batch processes which supply discontinuous heat, then you could integrate a storage to continuously generate electricity, and I will also have an example of this, this application. To show you the demand for Germany as an example, we have some consumers in the food and pulp and paper industry, higher demand, but the big three sectors in Germany for industrial processes is the chemical industry, the ceramic industry, and the metal production. So these are the three consumers, and as was shown before, they can be distinguished in terms of temperature level here. Now an example of a process of metallic process. This is an electric arc furnace for scrap steel. You can see here the picture, how the process looks like. It's in German, but I will explain a bit here. So there's the scrap at the bottom. You have the graphite electrodes. They are lowered into the scrap. And then you have a very high current, low voltage, and then you melt the scrap directly by electricity. And then once the scrap is molten, then you will pour the steel out, and you have some slag as well in the process. And you have a lot of flue gas here. And the typical way what they do is they don't use the heat in the flue gas at all, and the heat in the flue gas is between 15 and 35% of the heat input. A typical furnace maybe has 100 megawatt of electrical power. So you can imagine that you have a lot of flue gas heat here. There are some limited installation of root storage systems. So what they do, they have here, you can see a picture at the bottom, installed some heat exchanger in the flue gas stream here. This is a heat exchanger with direct steam generation. And then they inject it in a root storage system, and they couple this with an ORC process. But this process is not very efficient. It's expensive, the ORC. The root storage has a decline, so you don't have a constant temperature outlet of the root storage. So this is not an ideal solution. And we did in a project called Tessin, together with the industry, a study of integration of molten salt. This is not being demonstrated. This was a conceptual study here. And you would integrate similarly as here a heat exchanger for molten salt, and you can store the heat. You would need something like 100 tons of molten salt, not too much. The process time is short, maybe only 15 minutes, 30 minutes of storage. You don't need to have bridge very long durations, but then you could bridge this gap when you discharge here your furnace, and then you could run continuously a steam turbine. And with the calculation, it was shown that maybe about from the 100 megawatt, you could generate 5 megawatt of electricity constantly. This would be 5%. So these are the rough estimations of the process. So it could be attractive, was not demonstrated. We talked to different steel sites in Germany, but didn't come up with a further project here yet. We have another conceptual study for the chemical industry, also no demonstration yet, but there's strong interest, I would say, in the chemical industry. We had a project called TransTestChem, is a national funded project. Did also some publication on it. And the first difficulty was that the chemical industry was not very happy to share the data of their processes. So we specifically looked into the on-site utility infrastructure. So this is supplied with natural gas. It's connected to the grid. And then in the local power plant, they generate steam and electricity for the processes. We didn't look into the processes. We looked only in the generation. So on the right-hand side here, you can see the generation, the different components. There are gas turbines, gas boilers, waste heat recovery, steam turbines, and so on. And then we check different storage options. We looked at regenerator type storage, PCM storage, and also looked a bit on thermochemical storage, root storage, but also molten salt storage. Also looked at different integration points. And the best solution we came up was to use electricity, charge the storage, use molten salt storage, and then inject high pressure steam here in the line. And in this way, we can generate electricity and steam, and we have almost 100% of utilization on the discharge. And for charging, the efficiency is also very high. So this was the most promising configuration we find out. So this project is almost at the end. There are some publications to come up. Some are already available. Also shown here, we used a software called Top Energy to optimize the operation of the storage. We used annual simulation of the plant. So we had some profiles of annual steam and electricity demand. We had electricity generation curves from the grid over 1 year. And then we looked at OPEX reduction using this and also CO2 reduction. And you can see here on the figures, we looked at different years that you can get quite some significant CO2 reduction and reduction of the operational costs using such a storage system. I would like to conclude the talk. I talked a bit about Carnot batteries. I hope that I could show this is a solution working between short-term storage batteries and long-term storage power to gas to power. There's also a certain trend. If we look at the heat pumps, if we have heat pumps, we see higher costs, higher electrical efficiency, but lower TRL. If we have solution with electric heaters, we can basically already could outroll the technology. The technology is available in the end. The costs are lower, but the efficiencies are also lower as long as you don't use combined heat and power. Then about what could we do to improve competitiveness of these solutions with power to heat. It's interesting to think about repurposing of existing infrastructure. A steam turbine is basically a very expensive component. If you have infrastructure available, it's always useful to work in a brownfield. It's useful to increase the efficiency of Carnot batteries if you do some heat integration. I talked about combined heat and power, but you can also use integration of waste heat, and in this way you can also increase the efficiency. Then with the power to heat solutions for the process heat, I talked about the advantages for the chemical industry. They can reduce the OPEX and the CO2. But there's also a large use for the electricity grid, and nobody pays for it basically because we offer a flexibility solution for the grid, but the grid operators are not seeing this, in my view, at the moment. And also, if we compare this to pure power to heat systems, we can increase the amount of energy transferred from the electricity grid to the process heat via the storage. Because the renewables are available for a very short time only, we can charge the storage and the total amount of transferred energy will be increased. But these two advantages, 3 and 4, I think are not appreciated or seen by the grid operators yet. Of course, it's always interesting to look at multiple use cases. If we can, for example, not only have arbitrage income, but also other things that we reduce part load operation of some components, this always helps to have a better business case. We see some improvements in Germany about regulation, but there are still things to do to get these solutions in place. And of course, because we are researchers, we think that we can have a contribution as well with further research and development on this topic. And with this, I thank you and open for questions now. Yeah, Jana wants to ask.
Additional showstoppers, except from one we had that you see that to be removed, and there could be demonstrations.
So I'm not a legal expert about it, but this is really about paragraphs and exceptions of giving additional funds for some efficiency measures and so on, where certain technologies are considered and others are not. And what we really need there is openness to all sorts of technologies. People simply forget to, they think about batteries and power to gas and hydrogen and whatever, but not about our solutions. And then there's simply a missing paragraph or 2 additional words, sometimes enough in my view. And I'm not an expert which paragraph and so on, but that's at least what I picked up from the discussion, what is missing. So in the end, we need some lobbying to get the people there. And we have in Germany at least the association for storage. It's called BVES, the German Association for Storage, and we try to get this association to do the work and talk to the politicians and convince. But it's a long process. I think there were improvements already. We had, for example, in Germany, double taxation for storage. So you taxed by charging, taxed by discharging with the EEG in Germany. This is additional money you have to pay for the renewables in Germany. Also for the steam plant, when we had a project, if we would have generated electricity from the waste heat, the electricity generated would have been taxed 40% by the EEG at the time. So this stopped the project basically at the time. I think this is already stopped now, this regulation with the EEG, but some further improvements I think are still required there. I think these are mainly legal hurdles in my view. And of course, we need also, I think, to start demonstrating something in a reasonable scale. I think we cannot build something very large from the beginning, because also in the CSP sector, this has not been done. So first you start with a smaller system, then later on you size it to the upscaling of factor 10 or 100 or so. Because people need to see it works in this application, people need to learn about regulation and so on. So we also would need some first kind of demonstration in a smaller scale and to have some full-scale demonstration later on. That needs additional time, I think. And people are not aware that they cannot build a full-size system from the very beginning, I think.
And these questions, of course, it's a scientific and technological questions, definitely. But these questions actually, in the end, are those who might impair the development and the entry of different technologies, technological solutions into the market. I was a bit surprised about how little pumped hydro's capacity there in Germany. I would expect higher, actually. And my question, because this is the big player regarding storage and the electric system. Portugal and else. Where or not environmental concerns are being integrated in this system? Because of course, when we talk about pumped hydro, we are talking about destroying all the rivers, which is pretty much what we are doing. How far is this kind of question included in the discussion on which technology should be which technology should be posted?
So I repeat the question. The question was about the extension of pumped hydro and a very small installation in Germany of only 7 gigawatt in the moment, and how can it be extended and what is the social impact and so on. So first of all, we have additional capacity, not as Germans, but in Austria and Switzerland, because they have a lot of pumped hydro and we're going to use it. So, and they extended it at the moment already. So we make use also of this pumped hydro station in the neighbor countries in Germany. Also discussions with Norway. But in Germany, I think simply the resources, even without leaving all the discussion about the social impact and can it be done and are people against it and so on, we could maybe double it or something like this. I'm not, as a rough order of magnitude, I don't know the exact numbers. It's simply limited to the locations in Germany we have suitable for pumped hydro. So then the other idea is to use neighboring countries to extend it. And at the moment we don't see extensions in Germany of pumped hydro, which I don't understand, but I think it would be a good idea to start it. But we have a very strong, I think the Bundesnetzagentur, the people operating the grid, they're thinking about grid and grid and grid and not about storage. So then the question always is, who cares about the storage? Is it about the people generating the electricity? Is it about the people operating the grid? Nobody really cares about the topic, and it's not really clear who takes care and who is responsible for operation and so on. So at the moment we have a lot of discussion about grid extension, so that's ongoing and that's pushed very hard in Germany. But storage is a minor issue yet. But I think the storage is only an issue that people discuss about hydrogen, using hydrogen if we don't have the renewables. So of course it will play a role in my view, but it will be a rather expensive role. So we should take care not to minimize this use and to use other options as well. So. From the audience. Thank you.
Thank you. The last talk of the school, the second day of the school, before lunch. So. I will introduce Valeria Russo. She is a mechanical engineering and she holds a PhD in energy and environmental engineering at the University of Rome Tor Vergata. She has been a researcher in ENEA since 2004, and she works in the Renewable Energy Technologies Department in Solar Thermodynamic and Smart Network Division, and she is the head of the Solar Technologies Engineering Laboratory. In particular, she is involved in thermofluidodynamic analysis of components for CSP plants, in the modeling and designing of the same. She deals with the feasibility studies and creates performance evaluators models for CSP plants. Okay, so Valeria, you can start.
Thank you. Okay, good. Good morning to everyone. Today I'm going to talk you about the lessons learned from the commissioning and the management of CSP molten salt plant operation. Here we can see a little summary of the topic of this presentation. First of all, we talk about the principal problem in the solar field related to the high melting temperature of the molten salt. Then we will see the plant washing process, the molten salt storage system operation, and finally the startup and shutdown procedure. Okay, let's start with the principal problem related to the melting temperature of the molten salt. As we know, this value is equal to about 240 degrees centigrade. So it is mandatory to keep the temperature higher than this value in all the components of the plant, all the components crossed by the salt. And also during all the phase of functionality of the plant, for example, during the filling phases, in order to operate the component, or during the drainage phase, in order to maintain the temperature higher than the value of freezing of the salt. And also after an accidental salt freezing. In this case, in order to remelt the salt, solidify into the component. To reach this goal, it is possible to apply these three different methods. One method is heating by tracing the component with the heating cables. Another method is heating by Joule effect. And the last method is heating by armored resistance. For what concerns the electric tracing, here represented there is a picture of a common heating cable. The characteristic of the heating cable generally the cable are have a mineral insulation. And they have a stainless steel sheet and as a single conductor. Here in this table are summarized the main feature of the cable used in the solar field or a solar plant. And generally the conductor material is nickel chrome. The isolating material is magnesium oxide. The maximum temperature allowed is 600 degrees and so on. Here is the scheme of the cable, and it's possible to note the conductor resistive, the insulating, and the metal sheets. First of all, we have to keep in mind that the mineral insulated cable are constant power circuits only as a function of the operating temperature and not as a function of the length of the circuit that we have to heat. And then we have to consider also that when we want to dimension the heating circuit, it is necessary to know the operating condition and the geometry of the component on which it will be installed. So in order to dimensioning, first of all, we have to calculate the power needed to maintain at a certain temperature the component. To evaluate the resistance of the cable necessary to obtain the required power previously calculated. We have to evaluate also the specific resistance, and in this way we can choose the heating cable with the specific resistance that is closest to the value found. And finally, we have to check that at the operating temperature, the power dissipated by the heating element is that required. As a best practice, after the installing of the cable, it would be good to carry out some check, like for example a visual check of the good condition of the sheet, or some measurement. For example, we can measure the homing resistance or the absorber current or the power supply. Then we have also to check that the cable doesn't touch in any point. In fact, the minimum distance between the two sections of the heating cable must be around 10-15 millimeters. And finally, we have to check also the minimum bending radius that has to be equal maximum to 6 times the cable diameter. Here are some pictures of piping with solid salt inside. This occurs when the heating system doesn't work properly or doesn't be installed in the correct way. Now we can see how to install the electric cable along, in this case, along the pipe. Here is the scheme. How to fix the cable around the pipe. The cable must be fixed by metal clamps. And then there is a skin thermocouple, we can see here, used for the control of the temperature of the cable, the tracing tape cable. Obviously, the thermocouple must be installed in the coldest point. Here we have another example, another picture of the installation along the piping. Generally, the cable must be covered by a stainless steel sheet. And this solution avoid the contact between the cable and the insulation, in order to prevent from damage to the overheating of the cable itself. And also in order to create an oven-like effect to better distribute the heat along the pipe or along the component twisted. Here we have another aspect to consider when installing the tracing cable, is the correct position of the terminal part of the cable, the part not in contact with the pipe, but this part is hot. This hot part must be covered with a metal sheet in order to prevent the overheating. Here we can see in this picture we have the covered by a metal sheet. And here we can see an almost optimal realization of the coverage of this of the end part of the cable that goes out from the insulation of the pipe. Here we can see another example of correct tracing installation, especially on a valve. In this case, we have to install two electric cable, one on the body of the valve and another one on the bonnet of the valve. And as a consequence, we have also to install two thermocouple for the control of the temperature. Generally, the thermocouple positioned on the bonnet, the thermocouple is positioned on the bonnet because the bonnet is the coldest part of the valve. In this way, we can assure the movement of the valve in every time. Here is an installation in a real plant realizing. Here instead there is a scheme of the tracing of the vent valve and the relative piping. In this case, the vent piping must be traced for all the length. Because even if some salt goes out from the vent valve, the salt doesn't freeze, and so doesn't block the vent line. Another example of installation tracing is the draining valve. The vent draining, all the valve in general are critical components on a CSP plant. In this case, like in the vent valve, also the draining piping must be traced for the same reason of the vent valve, because so if it is tracing for all the length, it permit an emergency drainage of the solar field in any moment. Here this is a picture of a draining pipe inside with molten salt solidified inside. It is this happens because the tracing was not properly installed. Here instead there is a scheme of the tracing of an instrumentation lead, like for example a pressure sensor or a temperature sensor. In this photo there is a it is a pressure sensor. Okay. Finally, here we have some picture that show the correct arrangement of the cable on the tank. In this case, we have to install the electric cable both around the wall of the tank and on the bottom of the tank. And here instead there is a picture of the installation of the heating cable on a flange, because we know that the flange is a component that have a high thermal losses. So we have to put the cable very carefully. Okay, as said before, another system, heating system, is represented by the Joule effect. The Joule effect is applied on the loop of the solar field. In fact, due to the presence of the glass envelope on the receiver tube, it is impossible to install the heat tracing on this component. So the receiver is heated, and the receiver and all the line is heated by the Joule effect. In particular, we have an electrical generator that is connected to the ends of the line in order to create one or more links within which current circulate. Here are some indications for correct functioning of the system. First of all, in order to have a correct and uniform heating of all circuit, all the elements of the circuit would have the similar resistivity. Otherwise, the element with the major resistance will get hot and will have the possible overheating. Then all the instrumentation, all the pipe and component support must be electric insulated. And then we have to consider that it is possible to have a potential issue of local electric corrosion if the electrical connections are not designed and realized correctly. And finally, we have to pay attention to the resistance of contact, because in this point we can have the local overheating. Here are shown the electrical clamps connected to the receiver tube line in this picture. At this clamp are connected the cables coming from the generator. In this scheme, instead, there is represented the connection between the aluminum plate, shown in this picture, and the electric cable. It is very important to ensure an excellent contact between the end of the terminal of the electric cable and the aluminum plate, in order to avoid electrical dispersion. Here we have some example of installation of the electric lamp on the solar field. The correct way to install the electric clamp. If the electric clamp are not soldered in the right way, the aluminum plate can be overheated. And here we can see in fact a plate damaged from the overheating. Perhaps because in this case there wasn't a good contact between the surface. Again, another example of overheated terminals. Here we can see the rubber sheets burned. And the last picture of an overheated cable that is broken. Okay. Okay, it must be kept in mind that the components subject to electric heating, since they are crossed by the electric current, must be isolated from the rest of the structure. In particular, the support of the receiver tube, because the Joule effect is applied on the receiving line. So in this picture, we can note the green disc positioned between the tube and the structure. These discs are made of electrical insulating materials. In general, the material is a ceramic like aluminium, zirconia, or something like that. Another critical aspect for the management of the solar field with molten salt is represented by the melting of the solar salt freezed inside the component after an accident. In this situation that occurs obviously after an accident, or also after a failure of some component or a failure of the control system of the plant. In this case, there is a specific procedure that prescribes, first of all, the heating of the line. It prescribes that the heating of the line must be slow, and so the temperature rises uniformly throughout the circuit and the line. In this way, any mechanical stresses due to the increase in volume associated with the melting of the salt are avoided. If the procedure isn't applied, there is the possibility of having mechanical stresses, which can also lead to the breakage of the receiver tube, as seen in this picture. In fact, here is the glass tube is broken, and here we can see a little piece of glass inside the vacuum around the tube. Another activity that required to pay attention is the washing of the entire plant, solar field, and all the circuit. For this activity is used demi-water. The water is pumped by a dedicated external pump, and this in order to prevent any corrosion phenomena that could realize in the circuit. The cleanup processing residues can be done flushing and discharging the dirty water from the circuit. Then we have to drain the water using vent and drain pipes. And finally, we have to dry any residual water inside the circuit to avoid the flash evaporation during the first startup of the plant. This operation can be done flushing dry air and turning on the tracing on all the components of the plant. Here we can see some picture of different components after a bad washing. In fact, here we can see inside here is a valve. Inside this, the body of the valve, we can see some residual of the production process. And here we can see the damage caused by this residual. And here is the picture of the residual that were inside the valve. Okay, up now we have talked only about the possible problem related to the solar field. Now we can see instead the operation of the storage system. First of all, here there is a little list of the best practice for the design and the realization of the storage tank. For example, we have to consider that the tanks must be sized to hold the full inventory of salt. The minimum level of the salt inside the tank, it's at a level that submerge the impeller of the pump. We have to consider also to take into consideration the material expansion. So the floor and the foundation must be designed to handle the normal expansion of the tanks. Then we take into consideration the buckling effect, the friction between the tank and the foundation, and then we have to consider that the tanks are manufactured on site. So we have to have the quality control of the welding is essential. And then finally, we have to foresee a passive cooling system because we have to assure that the concrete under the tank doesn't reach the maximum allowed temperature for the material. Then we have to consider also during the mentioning of the system that the transient operation condition change the temperature very rapidly, increasing so the thermal stress in the shell and the floor of the tank. Then also the combination of the thermal stress and the friction can compromise the stability and the integrity of the tank itself. Usually the floor of the tank is fabricated by welding together rectangular plates, and so it is possible that the residual stresses and plastic deformation may be introduced into the floor. Finally, we have to install a passive cooling system in tank foundation. Here is an image of a possible system of cooling. The last process that we have to take into consideration is the startup and shutdown activity. In fact, in order to obtain an optimal management of the plan, it would be define the procedure because these two operations are quite delicate. For what concerns the startup process, normally, first of all, we have to turn on the tracing and setting the temperature at 290 degrees centigrade. After, we have to check the correct position of all the valve of the circuit. And when the set point temperature is reached, we can start gradually the pump. When the rated flow range is reached, at this time we can put the mirror on focus, online focus. And the plant starts operation in a normal condition. The same procedure can be done for the shutdown. In this time, we have to turn on the tracing on the vents, drain valve, and drain tank, in order to permit to the salt to drain in this component. After, we have to defocus the mirrors and stop the pump, so the circulation of the salt. And when the temperature on the tracing reached the value of the set point, we can gradually open the drain valves and the vent valves. So we start the drainage process of the whole plant. Okay, we have seen more or less the principal problem that we have encountered during the commissioning and during the first management of the plant. So I'll finish it. Thank you for the attention.
Just a more answer here.
I'm interested in the draining and filling procedure. Like the consider those two processes, which one makes you more nervous?
Which was, sorry?
Which one does make you more nervous? Is it more draining that's complicated or more?
More draining. Because,
The question.
okay. Between the two processes, the filling and drainage process, which are the more complicated process, right? Okay, I think that is the drainage process because the salt must through through the piping, the draining piping, and generally we have to take pay very attention to the temperature of this piping that normally are cold. So it can freeze in some points.
Thanks for the call. I also have a question about the drainage process, follow-up questions. How long do the tracing is switched on for drainage? Do you use additional measures to drain, for example, pressurized air or something like this? And how long do you keep the tracing on? Question.
How long time you have to?
So you drain, you keep it switched on, or you switch off when you stop the pump, or
No.
do you wait for some while?
No, okay, I have to repeat the question. Okay. How long tracing remain on during the drainage process? The tracing remain on until all the salt is draining from the plant in order to avoid any cold point in which the salt can solidify. For security, it's better to take on the tracing until the end of the process.
So you monitor basically the filling level of the tanks.
For the filling, we have to preheat the tanks, and then we have to melt all the salt, put the salt.
Or I mean, we drain.
Yeah.
You see the filling level of the tank, right?
Yes,
We drainage, so we get information. Which or how do you know when you?
I know when the drainage left the molten salt in the drainage tank reach a level that I know. It's in correspondence of the.
And you use pressurized air additionally?
No.
Or
Only vent valves and drain valves to all open, and the inclination of the solar field, obviously. Okay.
So with this direct heating of the pipes,
Yeah.
Is there any electrolysis or
No.
corrosion
No, there isn't.
increase or something happening, like any electrochemistry?
No.
happening?
No, there happened nothing.
So did you already monitor that, or can you make sure, or?
We have done some tests in laboratory, but we have not observed any phenomenon of this type.
More questions?
Have you tried induction heating for the use?
Sorry?
Induction
Induction heating, yeah.
for the receiver tubes. Have you tried?
No, the induction heating, no. Only the Joule effect. No, we have done, never tried. Yeah.
Okay. So we can thank again Valeria. So before closing the second day and also the online school with the the participant here in presence in Cassaccia. After lunch, we'll visit the infrastructure, the PCS and MOSE facility, and some, no, MOSE, no, sorry. And some facilities in some buildings in Cassaccia. I would like to ask to Pedro to close this call. And thank you very much to everyone who has attended this event online and in present. Thank you.
Well, thank you so much. Well, we end here our online session. We will still have some additional visits for the ones attending the fast track school on site. Thank you so much for your interest. This fast track school is one of the very important activities we are developing within SALTOpower in the framework of developing a career building framework within these three institutions, DLR, ENEA, and the University of Évora, and also within our research infrastructure, which is the reference research infrastructure in Europe for molten salt technology. So please stay tuned in the project. We will be using your contacts for sure to announce the coming editions of the Fast Track tool. There will be 2 more editions along the projects, so stay tuned and stay in touch. Thank you so much for the online attendance. Thank you so much for the presential attendance. Take care.